Hello, all. So I thought about starting today's lecture with a good chemistry joke, but it turns out that all the good ones are gone. Ah! All right, sorry, I know that's awful, but I had to throw it out there for you. So today begins our final unit in CHY 113. We are going to look at the properties of gases and gas laws. And then we'll move on next week to talking about something called intermolecular forces. We discuss gases and gas laws in particular, though, because it turns out that gases and the properties of gases are much more affected by the surroundings and affected by the conditions than liquids and solids are. And so that's really going to form a lot of the basis of our discussion today, is looking at how some of the properties of gases change as we change things like air pressure or temperature, volume, things like that. And so looking ahead at what we're going to be talking about today, there it is. Today we'll be talking about pressure in general, what pressure is. And then we'll move on to talking about gas laws, which is a discussion about how the properties of gases change with varying conditions. And then finally, what we call the ideal gas law. Next time, in the next lecture, we'll talk about how gases and chemical reactions, what was sort of the interplay there, gas mixtures, and a couple of different smaller topics involved with gases. And so when we think about gases in general, we know that gases, for one thing, can be compressed. And so this is something that's just sort of intuitive knowledge that you know, really. I mean, you can take a gas that has a certain volume, and you can compress that down to a smaller volume. Think scuba tanks. I mean, that's the reason that scuba tanks work. If I remember the numbers, and I'm probably not going to remember this off the top of my head correctly, but a scuba tank, for instance, is I think about 20 liters or so. Each breath that we take in is somewhere around, and this is where I'm definitely forgetting the numbers, but let's say it's around 2 liters or even a liter. And so that would mean that, if we weren't able to compress gases down, that a scuba tank would only contain enough air for about 20 breaths or so. Again, those numbers are definitely off, but the point remains that if we couldn't compress air, we wouldn't be able to put nearly enough air into scuba tanks in order for them to be effective at all. But since we can really compress it and really pressurize that gas in there, we're able to provide enough air in scuba tanks to last for a very long time. We also know that gases exert pressure on whatever surrounds them. So think of like a tire. There's air in the tire, and that air exerts a pressure on the outer rims of the tire. That's what keeps the tire inflated. Gases also expand into whatever volume is available. That's a key property of gases in general. We could have a gas that was in a container this big, and then if we're able to just expand the size of that container without changing anything else, we expand it to this big, the gas is then going to just fill this container. And so gases will always expand to whatever volume is available. Gases mix completely with one another. That's another important property. And so again, thinking of the air in scuba tanks, and somebody familiar with scuba, feel free to email me and correct me if I'm wrong here. But I'm pretty sure, for instance, that scuba tanks are not just filled with oxygen, they're filled with air typical of what we breathe. And that air typical of that air that we breathe is actually primarily nitrogen, some oxygen, some CO2, and some other trace elements in there. But even the air around us, the air that we breathe, mixture of lots of different gases that all just intermix and mix with each other. And so when we think about the physical properties of gases, when we think about the actual properties of a gas, the physical properties are going to depend on 4 basic properties. The physical properties will depend on the pressure, which we'll define in a moment, the temperature, the volume of a gas, and N, or the number of moles, the amount of the gas. And there's a relationship amongst all of these properties, which forms a big part of the basis of today's lecture. And so the physical properties will depend on these 4 basic parameters and these 4 basic properties of a gas. It is important to note that when we say, for instance, something like oxygen is a gas, what we really do mean there is that oxygen is a gas at what we would consider to be normal conditions of pressure and temperature. And so atmospheric pressure, room temperature, think the conditions essentially wherever you're sitting right now, quote, normal conditions. We know that oxygen is a gas. We can really increase the pressure on oxygen if we wanted to, though, really pressurize it a lot, really lower the temperature to get it into actually a liquid form. The oxygen that makes up some of the fuel for rocket boosters, for instance, the fuel that helps the space shuttle lift off. That's liquid O2 in some of those tanks, and so that's highly pressurized oxygen, enabling it to go into the liquid form. But again, when we do say that something is a gas, we're talking about normal, quote, normal conditions. And so pressure. What is pressure? Ultimately, pressure is defined as a force per unit area. And so we have a force of whatever, in this case, the gas molecules, pressing on a certain amount of area. One of the more common pressure units that you're probably familiar with, PSI. That's pounds per square inch. And so pounds, there's your force right there, per area, your square inch. So when we think of inflating our tires to 30, 35 PSI, that's what we're really talking about, is that the air in that tire is exerting a pressure of about 35 pounds on every square inch of the tire. This is an example here of they wouldn't look exactly like this, but what an early barometer would look like. This is going to measure air pressure. The air pressure would push down. This would be a little puddle of mercury right here. The air pressure, the atmospheric pressure, pushes down on the mercury here, causing the mercury to then climb up this tube, and the height at which the mercury is going to climb up is going to be dependent on the pressure pushing down. More pressure pushing down, the higher the mercury is going to climb in the tube. Less pressure, the mercury won't climb as much. That's why another measure of pressure that we have is mmHg, millimeters mercury. Because some of the very first instruments that measured air pressure worked exactly like this. And again, the actual instrument would have looked different. This is a schematic of really what's going on. But the air pressure pushes down, causing the mercury to rise to various levels, and they measured that rise in millimeters. And so a standard atmospheric pressure would cause this mercury to rise up by 760 millimeters. And this just explains everything that I was just talking about. And so the mercury rises up the tube until the force of the mercury pushing down from the tube equals the force pushing it back up coming from atmospheric pressure. So again, don't worry too much about that interplay of forces. Just know that basic concept of the more pressure, air pressure pushing down on the mercury here, the more it's going to climb up into the tube. Another way to really think about pressure, and unfortunately I don't have, actually, let me pause you for just one moment. Okay, and we're back. Another way to think about pressure, and a way to think about it that's really going to help us as we visualize some of these relationships, is to think of pressure as being the number of collisions of gas particles with the sides of whatever container that it's in. And thinking of pressure in that way, which is really the same way, it's still, when we're thinking of those collisions, we're still thinking of the force of those collisions over a certain area. Or that's what it really is. But it's helpful for us to visualize it in that way of just thinking of sort of that number of collisions, how many collisions these particles are having with the sides of the container. And so, for instance, and this is what I needed to pause to search for, let's take a look at this container here. So we can see a bunch of gas particles in here, all bouncing around. And sorry, I just wanted to see what options I had there, because I hadn't looked at that yet. So we can see all these gas particles in this container here. And we can see that they're bouncing, they're hitting each other for one thing. That's another of the properties of gases, is they'll hit each other and have what we call perfectly elastic conditions, or perfectly elastic collisions, which means that they don't lose energy when they collide with each other. They also don't lose energy when they collide with the sides of the container. And so just sort of take a look at the collisions here on the side of this container, and you can see that we have about 25 atmospheres of pressure. Atmosphere is just another unit of pressure. We're going to look at different pressure units in a minute. But ATMs are just a unit of pressure. 1 ATM is sort of normal atmospheric pressure. So picture if your normal atmospheric pressure at sea level. So picture a nice sort of average day in the summer. You're at the beach, right at sea level at the ocean. The air pressure right there is 1 ATM. And so let's look at what happens when we change some of our parameters a little bit here. And these are some of the relationships that we're going to be exploring and talking about today. But if I change the volume of this container, for instance, so right now we're at about 25 ATM. If I make this container bigger, you can see that we have fewer collisions with the side of the container. We haven't changed anything else. We haven't changed the amount of gas in there. We haven't changed the temperature. All that we've changed is the volume. And we can see that our pressure went down. And we can see, in fact, visually that we have fewer collisions with the side of our container. Another relationship that we're going to look at is the relationship between temperature and pressure. And we can see here that if we don't, again, we're not changing anything else right now. We're going to leave this volume the same. We're going to leave the amount of gas the same. But if we really start to cool this down, remember what temperature is really a measure of the average kinetic energy, the average motion of the particles. So we lower our temperature, we reduce our temperature, the average speed of the particles decreases, and we can see that definitely, in fact, we're getting fewer collisions with the side of our container here, which leads us to a lower pressure. Or if we heat it up, now we can see that our pressure is increasing, and watch the particles on the sides of the container. We're starting to get more collisions on the side of that container. Particles speeding up even more and more and more and more and more and more. And we're getting much faster movement, many more collisions with the side of our container. We now have a much higher pressure. So let's look at one more property of a gas. Now we're changing our volume. See how the pressure jacked up. I'm just going to lower the temperature back down a little bit. So one more thing that can affect the pressure. Actually, if we come back to our slide here, let's just take a look back. Which slide did I want? Sorry. There we go. So we talked about the physical properties being dependent on pressure, and we're looking at seeing what affects pressure right now. But the temperature and the volume, we looked at that. Now let's take a look at what happens if we change the amount, how much gas is actually in there. So again, we're back to a pressure now of about 20 ATM. Let's go ahead and just put a bunch more particles in there. We'll let those disperse, but now we can see what's happened to our pressure is it's increased. Now again, one of the things that I really like about this unit is most of these properties just make intuitive sense. If we're thinking about pressure as the number of collisions on the side of a container, if you sit back and you think about it for a second, if we add more particles, if we're not changing anything else, if we add more particles, that should increase our number of collisions. That's going to increase the pressure. If we decrease, if I let some of these particles out, then I'm going to be decreasing my number of collisions on the side of the container, and I've decreased my pressure. So again, we just think about these properties and they start to make sense for us. And so we've seen what these look like sort of in this qualitative way. More particles is more pressure, so there's a direct relationship. More temperature, higher temperature, there's more pressure, so there's a direct relationship. Increased volume leads to decreased pressure, so there's an indirect relationship. Now let's look at quantifying those. Let's look at using the gas laws to really quantify these relationships for us. Actually, first, let's just look at some of the typical units that we use. Atmospheres is a very, very common one. Like I said, sort of normal pressure is 1 atm of pressure. And you might have to do several different conversions depending on what you're given for starting information in some problems. But another fairly common unit of pressure is millimeters mercury. 760 millimeters mercury equals 1 atm. Torr is another pressure unit. 760 torr equals 1 atm. So note that relationship here as well, that 1 millimeter mercury equals 1 torr. Pascals are another fairly common unit of pressure. 101,325 pascals equals 1 atm. Quite often, just due to the size of these, we think if we're using pascals, we think in terms of kilopascals. And so that would be 101.325 kPa or kilopascals equals 1 atm. These others are used a little bit less frequently, at least in chemistry. 1.01325 bar is 1 atm. And then we have our pounds per square inch, 14.696 pounds per square inch, PSI, equals 1 atm. Typically, we'll be looking at either atmosphere or torr, maybe millimeters mercury or pascals. We don't typically use bars or PSI in chemistry. But any of these conversions here, we might be expected to use. And so these are going to be conversions that you're going to want to be familiar with. What do these all look like? Think back to some of the problem-solving techniques we've used all semester. These are just conversion factors. That's all that they are. And so if we just look at one example real quick. So one of our conversions that we saw was that 1 atm equals 760 millimeters of mercury. And so let's say that we have a situation where we're given 610 millimeters of mercury and we need to convert that to atm. Then we're just going to use it as a conversion factor, just like we've been doing all semester. And so we're starting with 610 millimeters mercury. We know that there's 1 atm per 760 mmHg. And so then we plug that in. We get 610 divided by 760. And using our correct number of significant figures, 0.80 atm. Note as well, speaking of significant figures, that since these are exact conversions, is exactly 760 millimeters per atm, exactly 760 torr per atm, and so on, that these are considered infinite significant figures. And so for your sig figs, you will always go back to your initial measurement. And so we were given 610 with our 2 significant figures. And so I used 2 significant figures here in my answer. But again, that's all these are. These are just conversion factors. Use them just like we've been using conversion factors all semester long. Let's just talk about temperature really quick. And so temperature, as I mentioned, and as we mentioned a couple times sort of indirectly through the course, temperature is really a measure of the speed of particles. Technically, it's a measure of the average kinetic energy of the particles. But really, in realistic terms, we can just think of it as of that average speed, the average speed that the particles are moving at. And there are several different methods of measuring temperature. We're most familiar with the Fahrenheit scale, where the freezing point of water is at 32 degrees Fahrenheit. The boiling point of water is at 212 degrees Fahrenheit, meaning that every degree is equal to 1/180th of the difference between freezing point and boiling point of water. Not real helpful in many different ways. Again, we're familiar with it because that's what we use here. And so if I tell you that it's 72 degrees outside, you have an intuitive sense for that, and you're able to sort of to know what that would feel like. Everywhere else in the world uses Celsius for their temperature measurements, where the freezing point of water equals 0 degrees C, the boiling point of water equals 100 degrees C, which means that every degree represents 1/100th of the difference between freezing point and boiling point. Makes a little more sense to base things this way. Again, so some of the basic measurements are based off these properties of water. And most all temperatures in science are going to be recorded in Celsius. And so when you're reporting the boiling point of a substance or the freezing point of a substance, we work with Celsius in any science measurements. When we're working with gases, however, we're going to introduce a new temperature scale here, known as the Kelvin scale. The Kelvin scale is what we call an absolute scale. Rather than sort of basing some of the numbers off the properties of water, the Kelvin scale being an absolute scale means that at 0 Kelvin, it's the theoretical point at which all molecular motion stops. And so again, remembering that temperature really is a measure of the motion. It's a measure of the speed of the particles. That means that theoretically, if we drop the temperature enough, there's going to be a temperature where that speed, where that motion just simply stops. That's 0 Kelvin. That's what we call absolute zero, is the temperature at which all molecular motion ceases. Think about what that really means. I mean, absolute zero from a theoretical standpoint is a fascinating number. And so like when we look at something like at our little simulation here, so we start really cooling this down. We're getting really cold now. We can see that the motion is really getting very slow. Getting much colder now. We're down to like, when we're going to see the conversion in a second, but we're getting down to like negative 270 degrees Celsius here. You can see even in a simulation like this, which is pretty realistic, it's hard to get down to absolute zero. It's hard to get down that far. So 1 Kelvin here. We can see that there's still a little bit of motion, and then 0. And actually it's still, so this, I don't like this simulation as much as I thought I did, because this is still showing motion and it shouldn't be. 0 Kelvin, the point at which all molecular motion ceases. So really this should be stopped. We shouldn't be seeing any motion of the particles. But it goes even further than that. When we think about the structure of an atom that we've talked about, or even the structure of a molecule. And so actually let me pull out, I still have them in here. Pull out some of my models that we used a few weeks ago looking at molecular shapes. Here we go. So here's a carbon dioxide molecule. And this is something that we didn't talk about in this course. It goes beyond the scope of what we need to talk about in this class. But here's our carbon dioxide. And even this molecule here, the carbons and the oxygens, aren't completely static. There's still some motion. There's a little bit of this, what we call bending, not to this extreme, but just to illustrate it. So we get some of this bending that goes on. There's some stretching, which I can't really do here, but there's some stretching along this bond. We'll get the oxygen actually does this, and some of that motion that happens. At absolute zero, that sort of motion stops. When we think about the atom itself, we have a nucleus and the electrons on the outside. That motion of electrons has to stop. The nucleus of an atom spins on its axis. That's something that we didn't really talk about. That's the basis of MRI machines, actually, is that nuclear spin. That has to stop. That's what absolute zero truly means. All motion stops. And so that's what the Kelvin scale is based on. It's based on that theoretical point at which all motion is just going to stop. It's a simple enough conversion. So anytime that we are working with gases, you do have to convert to Kelvin. Another thing and I'll look at that conversion in just a second, but another thing to mention is that Kelvin is not a degree type scale, which means that temperatures are reported simply as Kelvin, not degrees Kelvin. So for instance, we would say 273 Kelvin. We do not say 273 degrees Kelvin. And I'll be honest, it's a bit of a pet peeve of mine. I hate it when people say degrees Kelvin. It just grates on me like fingernails on a chalkboard. It's 273 Kelvin. The conversion is that we will convert, we simply add 273.5 to our degrees C. That gets us our Kelvin temperature. And so whatever our degree C is, add 273.5, that will get you to Kelvin. If you're converting from Kelvin to degrees C, then you subtract 273.15. And that might be fairly common too. You might have a question where you are asked to report where you're looking for the temperature and you're asked to report the temperature out. Through the calculation, you're going to be using Kelvin for the temperature, but to actually report the number out, we often will report it out instead in degrees C, just because, again, we have more of a frame of reference for that temperature. It means more to say degrees C to somebody than it does to give them the Kelvin temperature. Take a note as well when you are doing these conversions, just keep your sig figs in mind. And so when we're like this conversion here, 25.0 plus 273.15, it's an addition. So for significant figures, we're looking at where the decimal point actually is. And so we're going to cut off our conversion right here, which means that we would go from 273.15, or sorry, an answer of 298.15 to 298.2. And likewise, sorry, with our subtraction here, we're going to cut it off. Instead of 50.15, the Kelvin temperature was at 323, so we go to the ones spot, which means that our answer would have to be given to the ones spot as well. So just keep that in mind. Keep your significant figures in mind when you're doing your Kelvin conversions. But this is another thing that I really can't stress enough when we're looking at gas laws. Anytime with the calculations that we're about to talk about, anytime you have a temperature measurement, you must convert that to Kelvin. If you leave your answer in degrees C, you will get it wrong. Convert your temperatures over to Kelvin. Before we actually do talk about the gas laws, we need to just identify what we call standard temperature and pressure as well. Standard temperature and pressure give us this standard set of conditions that we can use for comparison purposes. All it means is if we talk about standard temperature and pressure, we're talking about a temperature of 273 Kelvin at 0 degrees C and 1 ATM, 760 torr. And so if you're given a problem where it tells you something about maybe you have a balloon with a volume of 4 liters at STP, that means that balloon has a volume of 4 liters at 273 Kelvin and 1 ATM of pressure. And so it's just a way for us to define the set of conditions and what we call standard conditions for comparison. Okay, so finally, let's now get into our gas laws. What the gas laws allow us to do is to define the actual mathematical relationships between the properties that we were looking at earlier. When we were manipulating our volume and temperature and amount and seeing the effect that had on pressure, we're now going to quantify that with these mathematical relationships. And so we're going to look at our relationships between pressure, volume, temperature, and the number of moles. First one that we come to is Boyle's law. Boyle's law establishes our relationship between pressure and volume. Boyle's law states that the pressure of a system, the pressure of a system of gas particles, so the pressure of gas, is inversely proportional to the volume, as long as the amount and the temperature stay the same. So in Boyle's law, we're assuming that the amount of the gas and the temperature remain constant. And in that case, the pressure and volume are going to be inversely proportional. And we saw that, again, we saw that here. So let's just bring our temperature back up to more of a normal. I thought maybe I could manually raise it. Let's just bring our temperature up quite a bit. Gonna take some time. Here we go. Let's go. Getting up there. I just want to bring it up so we have more collisions to make this little demonstration a little more obvious. Here we go. Now we're climbing. Okay. And so Boyle's law, our pressure and our volume are going to be inversely proportional to one another. And so now I have a pressure of 26, 27 ATM, that range. And again, this is where it helps if we really just think about what pressure is, the collisions on the side of the container. If I increase my volume, it stands to reason that I'm going to decrease my number of collisions, which would decrease my temperature. And that's in fact what I definitely see. I increase my volume, I have now decreased my number of collisions, and I've decreased my pressure. Decrease my volume. Now I have a lot more conditions and a lot more collisions, and my pressure goes up. And so Boyle's law, pressure and volume are inversely proportional to one another. We mathematically express that. Sorry, I'll wait for that little box to disappear. P1 V1 equals P2 V2. And so a typical type of problem with Boyle's law would be that you have some sort of sample of a gas where you're given perhaps the initial pressure and the initial volume, and then you're told that the pressure changes somehow, and you're asked to find the new volume. And so you would use Boyle's law in order to do so. And we're going to look at some examples in just a minute. But let's think about where this is actually applied, or some examples of this. Bicycle pump, perfect example. As you're pressing down on a bicycle pump, the volume of air trapped in that pump is reduced. And think about what happens. As you're pushing down on a bicycle pump, it gets harder and harder to push down, right? The pressure is increasing in there. Because as that volume that's trapped in the pump reduces, the pressure goes up. And it's that pressure going up which then forces it through and forces it into the tire. Note here with Boyle's law as well that there we go. That you can use any pressure and volume units. They just have to be consistent. And so in other words, if you're given a P1, you're given an initial pressure in millimeters mercury. That means that P2 must be in millimeters of mercury as well. If you're given milliliters for your volume, volume 2 must be in milliliters. And that would apply for whatever answer that you get as well. Let's say that you're given a certain pressure in ATM, you're given a certain volume in liters, you're given a V2 in liters, a new V2, and you're asked to calculate P2. Since P1 was an ATM, that means the ATM or the pressure you calculate for P2 will also be an ATM. So again, any units, they just have to be consistent from one side to the other. Another great example of Boyle's law. Think about this, what happens when a diver, a scuba diver, goes really, really deep. More gases, especially N2, end up dissolving into their bloodstream. Another law, gas law, which we're not going to talk about for our purposes, but Henry's law states that the solubility of gases increases with increased pressure. And so the more that a diver dives down and feels increased water pressure, more gas, more nitrogen especially, is going to be able to dissolve into their bloodstream. And so here we have a diver going deep, going down, going slowly, going down deep. And so more gases, more nitrogen is dissolving into their bloodstream. If they come back up slowly, then that's fine. The gases just diffuse, the N2 will diffuse back out of the blood, and they're fine. If, however, they come up too fast, so now they're coming up too fast and they still have that extra nitrogen dissolved into their blood, then let's think about what happens. They're coming from an area of high pressure, down low, down deep, to an area of low pressure. So let's think about the gas that's in their blood now, that extra gas that's in their blood. If they're going from high to low, pressure, that means the volume of that gas is going to what? So they're going from an area of high pressure to an area of low pressure. Volume and pressure are inversely proportional. So if they're going to an area of lower pressure, the volume of that gas is going to increase. The gas bubbles then become way too large. This is the bends. If you've heard about the bends, this is what it is. Divers go down deep, more nitrogen dissolves into their blood. They come up too quickly. That nitrogen is still in their blood. The nitrogen gas bubbles expand. Very painful. Death if it's bad enough. So a lot of ships that might have a lot that have a lot of divers, like maybe Navy ships, especially that are sending people down. They'll have pressure chambers on the ship in case somebody does have to come up too fast by accident, or if they have to for whatever reason, they can put them back into this pressure chamber and quickly ratchet the pressure back up, which would then keep the nitrogen in their system and then slowly change the pressure and sort of mimic that process of slowly coming up. But this is why the bends occur. Okay, so let's look at an example. So here we have a sample of nitrogen gas at a certain pressure, at a pressure of 67.5 millimeters mercury. It's in a 500 milliliter flask. We want to know the pressure of this gas sample when it is then transferred to a 125 milliliter flask at the same temperature. And so we're not changing the temperature, we're not changing the amount of the gas. All that we're changing is the volume. And so this is a Boyle's law example. The way that I would approach these problems, what I would do is first recognize that it is Boyle's law. We've got pressure volume relationship here. So go ahead and write out Boyle's law expression, the Boyle's law equation. The next thing that I would do is write out all the information that you're given. We're given an initial pressure, 67.5 millimeters mercury. We're given an initial volume, 500 milliliters. We're given a new volume, 125 milliliters, and we're looking for our new pressure. We're looking for P2. I literally do this when I do these problems. Let's see if I have, no, I don't still have it to prove it to you, but some scrap paper that I was working with yesterday as I was preparing this lecture, I literally wrote this on my paper the same exact thing here as I was problem solving this. And so I recommend that you do the same thing. It keeps everything organized in your head. And so we see that we have to solve for P2. What I do next is I manipulate my equation before I put any numbers in. So I just do my algebra to this equation to isolate P2. We can see that if we just divide both sides by V2, that'll do it for us. Then we're ready to plug our numbers in. So we're going to put in our P1 and our V1 and our V2. And we can see just unit-wise that that's going to work out. Milliliters are going to cancel. We'll be left with our millimeters mercury. So we can see it works out as far as our units. And then we can do it out. And so we get an answer of 270 millimeters mercury. So here's another example. So we have a 500 milliliter plastic soda bottle emptied and sealed in Peru at a certain altitude at a certain pressure. So then if we seal the bottle at those conditions and then come back to Portland at a new pressure, so we were at a pressure of 475 torr, we're now going to be at a pressure of 760. Our initial volume was 500 milliliters. We want to know the new volume. Go ahead and try this problem. Pause the video now, do this problem out, and see what you come up with for an answer. Hopefully you got 312.5 milliliters. If you didn't, go back and check, see what you might have done wrong. Our next relationship is Charles's law. Charles's law is where we're going to investigate our relationship with temperature. Sorry. And so we're not changing our amount, we're not changing our volume. But we can see if we start to lower the temperature, we start to lower the pressure. So Charles's law tells us that temperature and pressure are directly proportional to each other. If I raise the temperature, I raise the pressure. If I lower the temperature, I lower the pressure. And it's important to note here, like I was saying earlier, that we're talking about the absolute temperature. We're talking about the Kelvin scale here. We have to convert over to Kelvin. Mathematically, the way that we express this, V1 over T1 equals V2 over T2. And that's the way that we would use Charles's law. Always, 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 always convert to Kelvin. Convert to Kelvin, convert to Kelvin, convert to Kelvin. Volume can be any unit that you want, again, as long as it's consistent from side to side, but temperature must be in Kelvin. And we can see if we had a sample of liquid nitrogen, then we can see this at work. If we had balloons, and we freeze them in liquid nitrogen, they shrink. Because as the temperature goes down, the volume is going to shrink. So here's just an example to think about. So your lungs have a volume of about 5 liters. I guess I was off on my earlier conversation about this. Lungs have a volume of 5 liters at 5 degrees C. So we want to know what the volume is at 11 degrees C. And so first, just think, is it going to be larger or smaller? So we're increasing our temperature, which tells us that we're going to increase our volume. And if we actually did this out, we would find that our lungs have a volume of 5.1 liters. So our lungs actually have a bit of an increased capacity at this higher temperature. Let's look at an example of Charles's law. So we've got a 5 milliliter sample of carbon dioxide enclosed in this container at 22 degrees C. And now we immersed this into an ice bath at 0 degrees C. We want to know what the new volume is, assuming that the pressure is constant. So again, approach it the same way. We identify that this is a Charles's law situation. And so we write out Charles's law. We then write the information that we're given. We're given an initial volume of 5 milliliters, an initial temperature of 22 degrees C, final temperature of 0 degrees C, and we're looking for our final volume. Anytime that you're given temperatures for any of these gas law problems, and you write out your given information like this, the very next thing to do, just convert it to Kelvin immediately. Just do it right away. Just convert it to Kelvin. Then you've got it. You don't have to think about it again. But we see here that we need to solve for V2. We're looking for our new volume. So we need to algebraically, we need to multiply both sides by T2. And so V2 is going to equal T2 times V1 over T1. That's just the algebra of solving this for V2. And so then we can plug our numbers in, and we get 4.6 milliliters. Let's look at another example. So here we have another syringe, 12 milliliters at 25 degrees C. And then we, heat it up to 100 degrees C. So we want to know the new volume at 100 degrees C. So we're going to, like before, pause the video now and perform this calculation and see what you get using Charles's law. Hopefully you got an answer of 15 milliliters, 15.0 milliliters, in fact. Let's look at one more example. So here we have a syringe with 150 milliliters of air at 25 degrees C. Now what we've done is we've changed the temperature. We're going to decrease the temperature until we get a new volume of 140 milliliters. And we want to calculate the new temperature. So now we're looking for the new temperature. We're looking for T2. Pause the video now. Try this calculation, see what you get. Answer is 278 Kelvin, or 5 degrees C. Now, I'm sure some of you are sitting there right now saying, I didn't get that. I got a wrong answer. Let's look at some algebra real quick. And so this is a Charles's law problem. And so we have our V1 over T1 equals V2 over T2. We've got our given information. I'm just going to go, oh, no, we'll leave it there. Okay. Sorry, our given information, our V1 equals 150.0 milliliters our T1, 25.0 degrees C, or is that 298.2 Kelvin. And we're given our V2 at 140 milliliters. And we need to calculate T2. One of the more common algebra mistakes that I see here is somebody taking this expression. So we have our Charles' law expression here, and we need to now solve it for T2. A very, very, very common algebra mistake that I see is people just seeing this and saying, well, I've got V2 here, so I just need to divide both sides by V2. And so then I get people doing V2 or V1 over T1 V2, and they divided both sides by V2, so they think they're done. What that actually is going to give you is 1 over T2. And so that's not correct. That's not going to give us the answer that we're looking for. And so what you have to do is recognize here that T2 is down in the denominator. That's the thing we're trying to solve for, though. So we need to raise it up into the numerator. Those of you who are really skilled in algebra, you recognize this hopefully, and you saw it and you just did it. If you're still a little shaky and struggling with some of your algebra skills, what I would do in this case is first cross multiply. Cross multiplying should be something that sounds familiar to you. So we're going to multiply these two and set them equal to multiplying these two. So we get V1 times T2 equals T1 times V2. Now we've got T2 up into our numerator. Now we can divide both sides by V1. That gets us to what we're looking for. And then we can just finally plug our numbers in. We get our T1 at 298.2 Kelvin times our V2 at 140.0. Sorry, that's ugly. All over our V1. And we do that out, and we come up with 278 Kelvin. I'm just going to double check myself again, so I did this yesterday. Make sure that it is still coming out right. Sure enough, 278 Kelvin. And so check your algebra. Make sure that you are performing the algebra of these problems correctly. Let's look at how we actually find absolute zero, because it's experiments with Charles's law that allowed us to theoretically calculate actual absolute zero. And so again, if we think about our relationship, as temperature goes up, volume goes up. And so we could set up an experiment, a pretty easy experiment actually, where we just take some of these measurements. We have a sample of a gas, and we increase the temperature. And as we increase the temperature, we record the new volume at that new temperature, and we can plot this line. All right, pretty easy to visualize an experiment where we could plot this. What we can then do, once we have this line, is remember absolute zero is the point where all motion stops. It's also the theoretical point where volume would be equal to zero. So what we can do is extrapolate this line down to the point right there where volume is going to equal zero. At that temperature, that's absolute zero. So there we have it. That's how we can mathematically or experimentally determine absolute zero. Talking a lot today, more than I have in the last week or so because of the holiday. What we can also do is combine Boyle's and Charles's law together. And so we have Boyle's law, P1 V1 equals P2 V2. We have Charles's law, V1 over T1 equals V2 over T2. We can combine those together into what we call the combined gas law. P1 V1 over T1 equals P2 V2 over T2. All we're doing now is we're combining the two of them together. This gives us a way to now manipulate two of the different factors and find the effect that has on the third. And so you might have a question very similar to this one here, actually. So a scuba tank has 8 liters of air at 140 atm and 20 degrees C. We want to know what that volume is at STP, at standard temperature and pressure. So we're going to write out all of our given information. Our V1 is 8.0 liters, P1 140 atm, T1 20.0 degrees C or 293.2 Kelvin. We're given P2 1 atm, that's STP, is 1 atm. Our T2 0 degrees C, that's standard temperature, or 273 Kelvin. And we're looking for V2. I didn't write that in here, but V2 is our question mark. That's what we're looking for. So we're going to use our combined gas law. And all we're going to do now is perform algebra to this to isolate and solve for V2, which is what we're looking for. And so we do that algebra out, and we see that V2 is going to equal P1 V1 T2 all over T1 P2. We plug in our numbers. We get 1043.5. But then we have to correct for the number of significant digits. We have 2 sig figs in our volume here. So our answer, this is a good example of scientific notation being a good way for us to report the correct number of sig figs. 1.0 times 10 to the third liters. That gets us our significant figures. So maybe we also want to know how many moles of the gas that is at STP. For that, we can use something called the molar volume. It turns out that at STP, at standard temperature and pressure, 1 mole of a gas, any gas, doesn't matter what it is, 1 mole of any gas at STP will have a volume of 22.41 liters. That's an important number to know and to remember. 1 liter of any gas, regardless of the gas's identity, will take up 22.41 liters. And so we had 1 times 10 to the third liters, and so we just use our conversion factor. So 1 mole is 22.4 liters. We're going to use that as a conversion factor. So 1.0 times 10 to the third liters, 1 mole per 22.4 liters, means that we're going to have 45 moles of the gas. Now here's just an example problem here for you to try. And so we have an inflated balloon at a volume of 6 liters at sea level, which is 1 atm. It's allowed to go up in altitude until the new pressure is 0.45 atm. And during that time, the temperature goes from 22 degrees C to negative 21 degrees C. You want to calculate the volume of the balloon at its final altitude. So we have a balloon with a volume of 6 liters. We're changing the pressure from 1 atm to 0.45. We're also changing the temperature from 22 degrees C to negative 21 degrees C. We want to use the combined gas law to find the new volume. Pause the video now, see what you can come up with. Do not forget to convert the temperatures to Kelvin. And hopefully you got 11 liters. One last example. So we have a sample of CO2 with a certain volume at a certain temperature, which has a certain pressure. And we want to find, we move it into another flask. And when we do so, we have a new pressure and a new temperature. So we want to find the volume of the new flask. So again, pause the video now. We're using our, oh, sorry, jumped ahead. Hopefully you didn't see that. Pause the video now. See what you can come up with for an answer for the new volume. Hopefully you were able to come up with 117 milliliters. And if not, look at the setup here. Look at how things are set up and how we solved for V2. We have our conversions to Kelvin. And see what you can come up with. A couple other quick relationships to look at that we don't spend as much time talking about, but are still important. One of those is the Gay-Lussac law, sometimes called Amundsen's law. And that's our relationship between pressure and temperature. And so it should stand to reason, as we saw looking at our simulation here. When we were looking at this simulation, we saw that it was a direct relationship between pressure and temperature. which leads us to the mathematical relationship of P1 over T1 equals P2 over T2. And then we also have Avogadro's hypothesis, which tells us that leads to the molar volume, which tells us that equal amounts of the gas at the same temperature and pressure occupy equal volumes. And ultimately, this also means that volume and number of moles, volume and amount, are directly proportional. And we would see that expressed like this. So V1 over N1, volume 1 over the number of moles, equals V2 over N2. And so another thing that we've done, or the scientists have done in general, is sort of combined all of this into also what we call the ideal gas law. PV equals nRT. And so we're going to talk about how to know when to use this equation versus the others in just a minute. But PV nRT, the ideal gas law, gives us now a relationship between pressure, volume, the amount of gas, and the temperature. Also using something we call the ideal gas constant, R. There are a few different values for the ideal gas constant, but this is the one that we'll probably use the most often, 0.08206. Units are liters ATM over mole Kelvin. And here's Rangeley coming up to say hi because he loves the ideal gas law. Say hi to everyone, Rangeley. There he is. Still got his orange collar on for hunting season, but we can take that off pretty soon, can't we, buddy? Okay. All right. I need to finish this, so you come down here, and then I'll pay attention to you in just a minute, I promise. And so using this, if we know the pressure, if we know the volume, if we know the number of moles, then we could use the ideal gas constant to find temperature, for instance. And so as long as we know the gas constant's always going to be the same, there we go. This number R will always be a constant, so we'll always know this. But the ideal gas law means that if we know any of the other three values, we could find the fourth. And that's typically the way that you'll use it. And so remember that you're always going to convert to Kelvin. And be sure to use the correct R value. What I mean by that, let's see if I have it here. I do have it. There it is. There are some different R values. I guess the other one that you'd be most likely to use would be this 8.314, but even that won't be that often. We're mostly going to be using the 0.08206. That does mean that your volume, though, for the ideal gas law, must be in liters, and your pressure must be in ATM. So for the ideal gas law, always make sure that you're using liters for volume, ATM for pressure. Moles is only one unit, but then also Kelvin for temperature. And there are a few different ways that you might use the ideal gas law. And we'll see actually some more of those in the next lecture. For now, and this is where I'm going to leave you for today, you might be asking yourself, or sorry, here's an example question. We'll do that first. And so we have a gas in a 250 milliliter flask with a certain pressure at a certain temperature. We want to know how many moles that is. And so go ahead and pause the video now, see if you can come up with the right answer. And there it is. And here's just another example that's actually all done out. I'm not going to walk through this one, but go ahead and pause the video if you'd like, and make sure that you are able to come up with the answer to this question here. And then a last example, or I think this is the last example anyway. So an example involving tennis balls, usually filled with either air or nitrogen gas in order to get a certain bounce factor. And so we have a particular tennis ball with a volume of 144 cms cubed containing 0.33 grams of N2. We want to know what the pressure is at 24 degrees C. A little bit more difficult of a problem. For this one, remember that a cm cubed, 1 cm cubed is equal to 1 milliliter. So you'll have to take that 144 cms cubed and convert that over to liters. Then you're also going to have to take your 0.33 grams of N2 and convert that over to moles. So do those things and try this problem with the ideal gas law. Let's pause the video now and give it a whirl. All right, we're just going to bring you to right here while I finish up. Hopefully you were able to get to ATN. And so let's talk about when you're going to use the ideal gas law versus the other gas laws. Really, what it comes down to, there we go, is that the gas laws, Boyle's law, Charles's law, the Gay-Lussac, and the combined gas law, those are when you're comparing two different set points. Okay, sorry, now you're just being a little too distracted. Give me a minute, buddy. You're comparing two different sets of conditions. You have a before and an after, so to speak. That's when you're going to use Boyles, Charles, etc. And so you're told, for instance, what the volume is at a certain pressure, at a certain temperature, and those factors change. And so then you find a new volume, so a before and after. The ideal gas law is going to be one snapshot in time. So for the ideal gas law, you'll simply be told you have this certain pressure, maybe this certain volume, this many number of moles, what's the temperature? So it's just one set point in time, not a before and after set of conditions. And so keep those in mind. Lots and lots of practice problems for gas laws on the website. So we go to the website here. We're now in Unit 4. Unit 4 materials. There we go. Now somebody's getting cozy down here. So Unit 4 materials, we have lots of different practice problems. So some Boyles, Charles combined, and ideal gas laws. And so try some of those, give those a whirl, and go through some of this practice. And as always, if you have any questions, be sure to send me an email. But that is all for today. And so thanks for watching, and everybody have a great day.